Hey guys, welcome back to Math Savvy. Today we are going to be doing 50 integrals and we are going to be working through them. It's going to complete our Calculus 1 series. Maggie is going to be teaching you how to do all of these methods that I'm going to be doing. And then I am just here for some practice problems, and it's gonna be kind of slow and soft spoken and whatever. I'm super excited. I've been working on getting some awesome problems for you guys, and I hope this helps you with whatever you need help with. Here at Math Savvy, calculus is our religion, and we have studied integrals for a long time. We love it. Also, I might make some mistakes. Call me out on it. I need to be humbled sometimes, and I'm human. So are you. We all make mistakes, but c'est la vie. Let's get started, okay? Okay, question 1. This is a classic definite integral, and we are just going to be following the classic formula here. So, integral of x to the third is 1/4 x to the fourth. The integral of 2x is going to be 1/2 times 2x squared. Canceled out, and you know what? Since I'm crazy, I'm just going to erase that. And we have to evaluate this formula, or this expression, at 2 and minus 1. Find the difference. What do we get? We get 1/4 2 to the fourth, which is 16, minus 2 squared, which is 4. I meant to say 1/4 here. And then we do minus 1/4 times minus 1 to the fourth, which is 1. So we get 1/4 minus 1 squared, which is minus 1. Here we get 0, because 1/4 times 16 is 4, minus 4, 0. Here we get minus 3/4, which is equal to 3/4, period. Another classic, we get 5/4 x to the 9/5. I am so wrong. We get 5/9. X to the 9/5. Evaluate it at 1 and 0. And then we just get 5/9. 1 to the 9/5 is 1. 0 to the 9/5 is 0. So we just get 5/9. Good job. Next, we are going to do a little distribution, because that's going to make things a little bit easier, okay? So let's rewrite this. We get integral at 2 and 0, 2x plus another integral, 6 of x to the 6th, evaluated at 2 and 0. Of course, we have a dx here. Then we're going to evaluate both of these. The integral of 2x is going to be x squared, as we did in 2 problems ago. So we get x squared evaluated at 2 and 0 plus 1/7 x to the 7th evaluated at 2 and 0. So x squared evaluated at 2 is going to be 4. X to the 7th evaluated at 2 times 1/7 is going to be, what is 2 to the 7th? 128 divided by 7. Of course, 0 is 0, when you take it to the 7th power. So we're going to ignore the 0. And because we're math girlies and boys and theys, we are going to simplify this into one singular number. So we got can't really simplify this, but that's our answer. Next, we are going to rewrite this as well, so we can separate the x and the 1 into 2 separate integrals, because that's going to make things easier. So we get 1/9 x over root x dx minus, because of that minus, we get 1 over root x evaluated at 1 and 9 dx. Rewriting them again, we're going to get root x dx minus x to the minus 1/2 power. Because if you just write it that way, it'll be easier. Okay, let's evaluate this. So we get 2/3 x to the 3/2 there, by the classic definition of integrals, which honestly I should write this down. We have x to the n. The integral of x to the n is going to be x to the n plus 1 over n, or times 1 over n plus 1 plus c, if there's no definite. Now for the next integral, I'm going to get 1/2 x to the 1/2 evaluated at 9 and 1. Now we're going to pull out that 2/3 there. What is 9 to the 3/2 power? So what is 9? What is the square root of 9? It's 3, and then you cube that, that's going to be 27. And then 1 to the 3/2 power is going to be 1. And then is 3 minus 1. We get 2/3 times 26 minus So now I'm going to show you a little bit of something cool. We know this property. Oh wait. So you see that? I'm going to compare it to this. It's the same integral except for the 6. So we're going to rewrite that. 6 times 1/2. Zoom in a little bit. Root 3/2 integral. And then we get 1 over square root of 1 minus t squared dt. What is this? This is 6 times the inverse sine of t evaluated at root 3 over 2 and evaluated at 1/2. What is the inverse sine of root 3 over 2? So using the trusty way that I know about the unit circle, which here's a video of Maggie talking about the unit circle. Alright guys, so I made a little oopsie doopsie here, so I am rewriting all of this out. So sine of pi over 3 is root 3 over 2. Sine of pi over 6 is 1/2. So then I plugged that in. We get pi over 3 minus pi over 6 is just pi over 6. Canceling out, we get pi, period. We're 1/10 of the way there. Congrats. I'm so excited to do the rest. Anyways, so here we are. We have 6 times the integral of nothing, or the integral of 1, is going to be x. So this is going to be 6 times x evaluated at 5 minus 2. We get 6 times 5 minus 2. We get 42. And just a little side note, what is the goal of an integral? It is to find the area under a curve. And then if this is our curve, which is going to be that thing, we're finding the area from -2 to 5. So we're finding this area. And what is that? That's a rectangle. So an area of a rectangle is base times height. The base is going to be 5 minus -2, and the height is going to be 6. So that makes sense how we got that, okay? That's the most basic integral possible, which is freaking awesome, you know what I mean? Okay, trigonometry. The integral of cosine is sine, always, because the derivative of sine is cosine. So this is going to be sine. Oh, we can't be using green here. This is going to be sine evaluated at 2 pi. Sine of 2 pi is going to be 0. Pi is going to be 0 as well. So period. Sorry, I got carried away there. Next, the integral of secant tangent is going to be tangent. That's not true. The integral of secant tangent is going to be secant. You know, that's the truth, okay? That's the truth, I promise. So this is going to be secant pi evaluated at pi over 4 and 0. Secant is 1 over cosine. Okay. I have this up for me. Okay, look at that. 1 over, oh no, here we go. A over x, or a to the x. The integral of that is going to be a to the x over ln of a over the log of a. This is going to be 10 to the x over log of 10, evaluated at 1 and 0. I don't know about you, but I don't know what the heck log of 10 is. So I'm just going to take it out. So 10 to the x, 10 to the 1 power is going to be 10. 10 to the 0 power is going to be 1. So our answer is going to be 9 over log of 10. F of x dx. So when it comes to problems like these, we are paying attention to the interval on the integral. So we see that we're going from 0 to pi, and this function goes from 0 to pi, but it changes at the halfway point, right? So we are going to have to separate this integral into two because they are going to be different values, right? For the first part, let's rewrite this. We have from 0 to pi over 2. This is going to be sine of x dx, right? Because that's what f of x is at those values. And then we have from pi over 2 to pi, that's going to be cosine of x dx, because that's what the function is at those values. And then we solve this as we would. We get minus cosine x evaluated at pi over 2 and 0. We get sine x evaluated at pi and pi over 2. Rewriting this, we get cosine of pi over 2 is 0, cosine of 0 is 1. We're going to get minus 0 minus 1 is going to be minus 1, so that's just going to be a 1. I'm just going to erase these minus signs. And then sine of pi is going to be 0, and sine of pi over 2 is going to be 1, so we get 0 minus 1. This is going to be minus 1. And then we get 0. That is our final answer here. Good job. For something like this, we're going to want to separate these three things because obviously it's going to make it a little bit easier. So we're going to do all of these separately. Okay, and we already know how to do all of these things. And then this is going to be tangent inverse of x. Because that's just something that we know. Plus c. Yes, period. Yes. Same thing here. We're going to want to separate these two things. The integral of cosecant is going to be, or cosecant squared is going to be cotangent as seen here. So once again, we're separating. And this is going to be cotangent. Wait, is it cotangent or negative cotangent? Negative cotangent of t minus 2e, the integral of e to the t is e to the t, plus c, minus cot t minus 2e to the t plus c. Okay, similar thing here, we're going to distribute, so we can separate these things so we don't have two factors. We get secant squared of t dt plus tangent t secant t dt. This is going to be tangent t plus secant t plus c. Yes. Okay, this is a little bit of trig substitution here, okay? Sine of 2x is going to be 2 sine x cosine x. And I know that because look at this little sheet that I have. I got this little thing going on here. And we know that big time. So I'm going to plug that in. Here we get 2 sine x cosine x over sine x. And that beautifully cancels out the sine x. So your goal with a lot of trig substitution problems is going to be to make it into something that is easily solved. Make it into something that we can solve, like these 6 problems. And usually if you're getting asked this question in class, there is a way that you can. So we get 2 sine x plus c. We're doing a similar thing here, distributing, similar thing to a couple problems ago, distributing x times root 3x, or the third root of x is going to be x to the 4/3 dx plus x to the 5/4 dx. We know how to do this by our classic integral algebra equation formula. So we're going to get 7/3, so 3/7 x to the 7/3 evaluated at 1 and 0, plus x to the 9/4 times 4/9 evaluated at 1 and 0. We get 3/7 times 1, because 1 to any power is itself, 0 to any power is itself. We have 4/9 for the same reason, and we're going to combine these because we're slaying, if you will. We got 55/63. Period. Another simple trig substitution problem here. For this, I'm just going to separate these two things, and by dividing by the cosine squared of x. So we have 1 over cosine squared of x d theta. Obviously, I didn't mean to say x, I meant to say theta, I swear. And then we get d theta, because cosine squared is canceled out in that second problem. So what is 1 over cosine squared? That's going to be secant squared. And the integral of secant squared is going to be tangent of theta evaluated at pi over 4 and 0. And then we just get pi plus pi over 4 from that. Tangent of pi over 4 is going to be sine of pi over 4 over cosine of pi over 4 is how I remember it. Sine of pi over 4 is going to be root 2 over 2. Cosine over 4 is going to be root 2 over 2. So we get 1. Sine of 0 is going to be 0 over whatever. It's just going to be 0. So we have 1 minus 0 there, plus pi over 4. That's going to be 1 plus pi over 4. We get 5 pi over 4. Next. Okay, absolute value. Absolute value is going to be an interesting thing when it comes to integrals, because of the property that the absolute value function can never be negative. So our goal with this idea is to find where the function is negative and find where the function is positive, separate them into two separate integrals. Where the function is negative, it's going to be a negative integral. You're just going to put that negative in front of whatever's inside the absolute value. And for the positive, you just treat as it is. You treat it as it is for the cosine function inside the absolute value. So here I'm going to separate these two things because that'll make things easier, because the one is going to be an absolute value and one isn't. So we get I'm just going to solve this first one right off the bat to get it a little bit more simplified. And then here we're going to have to separate the things. So the absolute value x, where is it negative? It's going to be negative from -1 to 0. And that is going to be the minus x function, because you take whatever is inside of the x function and you put a minus in front, or of the absolute value function, put the minus in front. And then for everything else that's positive, it's just going to be the normal thing here. Okay, 1/2, and then we get 2 squared, which is 4, minus 1 squared is going to be -1. We get -2, and we get minus 1/2 x squared evaluated at 0 and -1 plus 1/2 x squared evaluated at 0 and 2. Solving all of this, we get 3/2 minus 2 times 0 minus -1 is going to be 1, so we just get 1/2, or 0 minus 1 is going to be -1, and then we multiply that by -1/2, so that's going to be positive. And then we get 1/2 x squared, so 2 squared is going to be 4, minus 0, so that's going to be 2. We get 3/2 minus 2 times 5/2, cancel that out. We get 3/2 minus 10/2, we get minus 7/2. Period. Good job. We see a sign on, okay. 18. We see a sign on top, so I'm going to factor that out, see what happens. Okay, so 1 plus tangent squared theta, we have this property here. If we move the tangent to the other side, 1 plus tangent squared theta is going to be secant squared theta. So we have sine theta secant squared theta over secant squared theta d theta, boom, boom, period. Thus, this became an easy problem, didn't it? Minus cosine of pi over 3 is going to be 1/2. Cosine of 0 is going to be 1, so we have 1/2 minus 1. That gives us 1/2. 19. Okay. So now we have to see where sine is negative. Where is sine negative? Sine is positive from 0 all the way to pi. It's negative from pi all the way to 3 pi over 2. So 0 to pi, we have sine x dx plus pi 3 pi over 2 minus sine x dx. Solving this, we get minus cosine x evaluated at pi and 0 plus cosine x evaluated at 3 pi over 2 pi. Minus cosine of pi is minus 1 minus 1. We get 2 here. Cosine of x, cosine of pi, 3 pi over 2 is 0, minus cosine of pi is negative 1. So we get 1 here, because cosine is 0 minus negative 1. It's going to be 1. That gives us 3. I hope I didn't make any mistakes there. I sure hope I didn't. Sorry guys, had to take a break to pick up some Starbucks, obviously. Okay, let's continue. So we have something that looks like this. This is where we are going to talk about the u-substitution method of integration. With u-substitution, we are going to look for two things. We're going to look for a function that is kind of making things complicated within the integral, and then that function's derivative that can be factored out of the integral. For example, we have something like log of x. What is the derivative of log of x? It is 1 over x dx. We can pull out that 1 over x dx, okay? And that makes things a lot easier. So let's make that substitution. So we have u squared du, because we can pull out that 1 over x dx. We know how to solve that. We get 1/3 u cubed plus c. And since we're perfect, we plug in that u substitution once again, okay? So with this one, we have something that is making the function that we're integrating complicated, this cosine of t. And the derivative is this, but the negative of that. So there we go, we found our u. Let's do it down here. U equals cosine of t, du equals minus sine of t dt. Sine of t dt, which is what we have in there, is going to be minus du. Sorry, I hit the mic, bad girl. We have e to the u times minus du. Pull out that minus, and we get minus e to the u plus c. Plugging the u back in, period. Simple, right? We have the derivative of cotangent, which is in this complicated position here, and then we also have the derivative function in there. So we already know that the cotangent situation is going to be the u substitution. And usually with how these problems are set up in calculus classes, the u that you're going to choose is going to be in a complicated position. It's usually not going to be something like that. And this is making things complicated because of the square root. So we're just going to do that. And then we have cosecant squared x dx is going to be minus du, because that's what we have right there. When we rewrite this, we get square root of u times minus du. We get minus 3/2. Just kidding. That was a joke. That was a funny joke. 2/3 u to the 3/2 plus c. Plug it back in. And boom. Okay, so this is when it gets a little bit more complicated. So we're looking for something, for a function that has its derivative easily accessible to factor out. This is easily factored out. All right, guys, I lost my video, the tragedy, but here's the rest of the problem with just my voice. Sorry. So something with the second degree should be the u, because we can easily factor out the x dx. Does that make sense? U equals x squared. And the reason why you can't do 1 plus x to the 4th is because the derivative of x to the 4th is 4x to the 3rd. And that just makes things more complicated because you don't have an x to the 3rd factor that you can easily factor out to get that du. Do you know what I'm saying? So du is going to be 2x dx. And then we have x dx, which is going to be 1/2 du. Rewriting that, we get 1/2 of 1 over 1 plus u squared, because u is x squared, and then x to the 4th is u squared. You get that du. because that half du, that 1/2 outside, yeah, that du right there. 1/2 inverse tan of u plus c, plugging the u back in, 1/2 inverse tan of x squared plus c. Good job, my friends. Guys, I had to cut the video into 2 parts because I want to make things easier, and so the video isn't like a million hours long. So stay tuned for part 2.